Today's episode was sponsored by Kraken Rum. The mythical beast known as the Kraken is one of the most menacing, enigmatic, and powerful sea monsters humans have ever dreamt up. Back, I say, not yet, yar! In stories and tall tales, they prowl underneath the ocean waves, snacking on fish and pirates and occasionally using their powerful tentacles to pull entire ships under the waves. But how strong would a Kraken really have to be to do that? Your conception of what a Kraken is and does is probably somewhere between Pirates of the Caribbean and Clash of the Titans, but Krakens have been circulating popular culture for centuries, starting in myths and legends and reports, eventually making it into everything from movies to video games to Magic the Gathering. The description of a Kraken varies, but what is consistent is their ability to pull ships underwater. Is there a way to realize this strength with physics? Well, yes, everything can, but first, what is a Kraken? A Kraken was first rigorously described in literature by fancy boy Erik Pontoppidan in 1752 in his A First Attempt at a Natural History of Norway, where he said these creatures were sometimes so big that they were mistaken for island chains and it is said that if the creature's arms were to lay hold of the largest man of war, they would pull it down to the bottom. He probably doesn't sound like that. Now, don't be mistaken. It sounds far-fetched, but at the time, these reports were taken very, very seriously. We now know that these reports were probably just people seeing giant squid or volcanic activity making islands out of nowhere, but that's fine. We can still focus on how hard it would be for a Kraken to pull something underwater. Pulling a ship to the bottom of the sea would take almost an unfathomable amount of oomph, and the reason why starts with Archimedes' Principle. Archimedes' Principle states that the buoyant force on an object submerged in a fluid equals the weight of that fluid that object moves out of the way. For example, if the weight of fluid that is moved out of the way by a ship is larger than the weight of the ship itself, the ship floats. That's how they do it. But this tension between the buoyant force and the weight of an object in fluid is exactly why it is so hard to pull an object fully underwater. Here, let me explain. No, really, let me explain. The buoyant force on a submerged object can be substantial, but you probably already know this if you've ever played with a beach ball. Why is it so hard to force a beach ball under the water? Well, that's because to do so, you have to move a beach ball's worth of water out of the way, and water is very, very heavy. For example, for a beach ball this volume, I'd have to force the same amount of water out of the way as I weigh over 50 kilograms, over 150 pounds. And then you ride it away. If that's how hard it is to pull a beach ball under the water, just imagine how this scales up to pulling an entire ship under the ocean. That's something that we can figure out, but we need the same data for large ships that we had for the beach ball. Calculating the internal volume of a beach ball is easy. Calculating the total internal volume of something as complicated as a ship is much harder. But the best estimation that we have of that value is called gross tonnage, which is a non-linear measurement of a ship's total internal volume that scales with size. We can use this value to calculate how much water will be pushed out of the way if a ship is fully dragged under. But we don't just need the ship's volume, we need the weight of the ship too. This is called a ship's displacement, and it's equal to the weight of water that is pushed out of the way while the ship is floating. Since floating means that the buoyant force is canceling out the weight of the ship, displacement is the weight of the ship. We need this value because it makes a ship either harder or easier to drag under. Okay, so all we need to do now is pick a ship, multiply its total gross tonnage by the density of seawater and gravity, and from that value, subtract the weight or displacement of the ship. This will give us the total Kraken force, or the force required to fully submerge a ship's volume. All right, now it's time to release the Kraken. It sounded cooler when Liam Neeson said it. I'm gonna assume that our Kraken doesn't break any ship apart because if the ship is whole, that's what will take the most force. This is the Earl of Pembroke. It is a decently sized sailing vessel that was modeled after the ship that Captain Cook used to discover Australia. If we use this ship and these numbers I could find for it, for its gross tonnage and its displacement, then a Kraken to fully submerge the ship and overcome its buoyant force would have to pull with over 4 million newtons, or 900,000 pounds. This sounds like a lot. And it is. But if a blue whale could pull with all of its body weight, it would only take 2 of them to sink the Pembroke like a Kraken. Although whales probably can't pull with their whole body weight, so it would take a lot more. Still, Krakens are supposed to be dozens of times longer than a blue whale, so this situation is plausible. How about something a bit bigger? This is the Titanic. You know the Titanic. To meet its end by Kraken instead of by iceberg, the mythical cephalopod would have to pull down with over 1 billion newtons of force, over 250 million pounds. This is more force than the estimated force of all of the photons hitting Earth. It's a lot. What about a class of ship with more gross tonnage than any other? This is a Battleless class supertanker, and it's over 0.5 kilometer long. Let's do the math one more time. To pull down this beast of a ship, a beastly Kraken would have to exert over 2.5 billion newtons of force. This is equivalent to the thrust force of over 100 SpaceX Falcon Heavy rockets. If a Kraken could do this, it would have to make it one of the strongest mythical beings ever. So how strong is a Kraken really? Well, this island-sized monster would have to exert either millions or up to billions of newtons of force to drag ships to their doom, making them incredibly formidable fictions. And if they were able to do this, either with powerful mantle jets or just strong tenties, then they would be pulling better than our best rockets can push. But of course, if they were really smart, they would just break the ships apart beforehand and negate all that buoyancy. Strong and clever. That's what makes them so scary. Because science. Today's episode was sponsored by Kraken Rum. To release the Kraken, visit krakenrum.com and sign up for the League of Darkness to receive discounts, gifts, and special privileges. Safe travels, my friends, and please remember to always drink responsibly. Thank you so much for watching, Matt. If you want even more silliness, you can check out Musquatch. Or if you want even more science, you can check out the space program on ProjectAlpha.com, where if you sign up, you can also get Because Science 2 days earlier. Thanks again.